Is on? So good morning, and I'd certainly like to thank the organizers, which apparently includes me too, but for the opportunity to speak here and to invite me to Singapore. It's wonderful to be here. I've never been here before. So I was asked to give a sort of a review type talk, at least that was the impression I gave. It's very similar, I have to admit, almost identical to the one I gave in Durham, so if you've seen that before, I apologize. Although, depending on how it goes, I might try to say some controversial, unfounded statements at the end, just to stimulate some discussion on the proviso that you don't bite my head off. Well, you can do it gently, I guess. So the story I want to paint for you is a recollection of the story, well, of what we learned about M2's, and in particular, because this is sort of like a mathy audience, I want to focus on the role of these three algebras, which, nobody really talks about them anymore, and there's reason for that. But there's also reason not to forget what their role is, and I want to try to emphasize what their role was in the construction of M2's CFTs. And, well, let me just say that now. Then the second part of the talk is M5's. Now, of course, I can't review M5's because we don't know what they are. But I can discuss various things about the M5 brain. And in particular, I'll go through quite a bit of time about why we don't think that there is a nice, simple Lagrangian description. Of course, people once said that about M2's, but actually you can't find anybody who now admits to that. But people certainly do admit to the fact that there's no no Lagrangian description of M5's. And they have various arguments, and I will go through them, and various discussions about the M5, and like the title says, it's hopes for M5's. What might we learn? And maybe we could some applications of M2's. And of course, one does expect there to be relations between M2's and M5's from various stringy, well, M-theory dualities. And then what I hope to do, but it depends on time, is I want to ram some of my own stuff down your throats, which is a realization of the 2,0 system and some things about it that I think could be of interest to people, and I'd like people to tell me what they think about this system and if they see anything deeper in it than there currently is. Sorry, how do we do it? Oops. Yeah. So, in more detail, the outline is simply this. So I'm going to discuss aspects of M2's and the role of three algebras and M5's. But when I talk about M5's, I'm really going to be talking about the idea of constructing the theory in 6 dimensions. So there's a vast amount of literature, beautiful literature, which I will not discuss. Yeah? So I will certainly not be discussing all these stories about what happens when you reduce the 2,0 theory on some kind of manifold. So these novel non-Lagrangian field theories, duality, surface operators, AGT, this is a wonderful story, but I'm not the guy to give you a review talk on it. There's also other approaches, which I will not discuss. So relatively recently, in the last maybe 2 years, there's been some success in ideas in doing bootstraps for the 2,0 theory. And I give you these authors. And there's not that much on ADS-CFT of the M5 brain directly, partly because you don't know either side of the dictionary. But there have been some recent papers, too, about ADS-CFT. But I will not mention ADS-CFT one bit after this slide. And, of course, that's not because I'm against ADS-CFT at all. But the idea, in my mind, the challenge that the M5 brain presents us with is to define the CFT as a field theory that any quantum field theorist could understand. And of course, if you use ADS-CFT, you're kind of cheating because you're defining it by a duality, which you don't know how it works. Do you? No. Well, you know a large n limit. So to say anything more than just representation theory, you're basically looking at you need to go beyond the 1 over, perform the supergravity approximation on the left-hand side and some kind of interacting non-free theory on the right-hand side. And you don't know either one of those. That's what I meant. So for my colleagues, and it can't just be me, who's jet-lagged and you fall asleep during this talk, let me tell you what you can ask me later on over beers. So M2 branes are quite well understood, and yes, there's a Lagrangian, but it doesn't work the way as neatly and simply as one might have liked, as it does, say, for D branes. They're still quite intricate, and in particular, there's an important role, in fact, a crucial role, is played by these monopole operators, which are what you might call quantum or operators in the gauge theory. They don't really exist in the classical theory, they only exist in the quantum theory, and if you don't include them, you don't get the right answers. As far as the M5 branes are concerned, they are hard and they are not well understood, but I didn't list it here, but I think there's still hope that one can learn something new, even if it's not about the M5 brane. You'll learn something new. And then a third thing is, I think there's more to explore in these structures. And in particular, I think perhaps in the relationships between M2's and M5's. Okay. So let's start from the very beginning about M2 branes. So formally, the M2 brane superconformal field theory is defined as the strong coupling limit of n D2 branes. And of course, a strong coupling limit in 3 dimensions is an IR limit. So it's the IR fixed point of 3D maximal super Yang-Mills. So MSYM is maximally supersymmetric Yang-Mills. Of course, the whole idea is you lift this to M theory. So you embed that statement into string theory, and then you go to strong coupling, which means that you then lift to M theory. And M theory has 11 dimensions. And what happens, of course, is the SO12 Lorentz times the SO7R symmetry enhances to SO12 Lorentz times SO8. You have a 2 plus 1 dimensional object in 10 dimensions here, and it embeds to a 2 plus 1 dimensional object in 11 dimensions here. And all you have to observe is the 1 plus 2 plus 7 is 10, and 1 plus 2 plus 8 is 11. That's some high-level mathematics, which lead to a dramatic prediction, right? Which is that the IR fixed point of 3-dimensional MS Yang-Mills, if I say Yang-Mills, I mean maximally supersymmetric Yang-Mills, enhances from an SO7R symmetry to an SO8R symmetry. Yeah. What I find interesting, and I go around telling people this is M theory predictions, right? These aren't predictions that you measure in the LHC. These are predictions that you will measure in the sense that you should be able to go discard everything you knew about M theory or string theory and return to ordinary quantum field theory. You could go talk to your condensed matter colleagues. You could even go talk to your phenomenology colleagues, and you could tell them this is what should happen in this quantum field theory. And this is not so surprising, but it is a prediction. The M5 brane is more surprising. Okay. So, as we said, the relevant theory has now been constructed. So I was involved with the first construction, so-called BLG, which is maximally supersymmetric, meaning that the Lagrangian has maximal supersymmetry. So maximal manifest supersymmetry. Of course, it's restricted because it has only this one gauge group, well, technically 2 gauge groups. It's got one Lie algebra, SU2 plus SU2, and then as far as the global group is concerned, it's actually got 2 choices. And it's now understood that it describes only 2 or sometimes 3 M2 branes on an orbifold. It has a k, an integer. All of these theories are parameterized by an integer k, and this is for like k equals 1, 2, 3, and I think even 4, 1, 2, 3, excuse me. And then above 4, it exists. It has a Lagrangian. It has a weak coupling limit, but it's not clear how it relates at all to M theory. And that would be one interesting thing, actually. One of my wish lists is, does this have any meaning in M theory for large K? But the main player now is the ABJM theory, which you sacrifice a little bit of the manifest supersymmetry. You go from full 16 supersymmetries to 12 supersymmetries. So that's the famous ABJM model, or ABJ, if you drop Juan's name off. The gauge groups here are UN times UM, or UM, and let's just assume that n is the smaller one, and then it describes n less than m branes in an orbifold. I won't spend too much. So the ABJ ones are when n is not equal to m. I won't spend much more time, probably any more time on them at that stage. And actually, there's now sort of a zoology, it's rather curious, of Chern-Simons matter theories. These are all Chern-Simons matter theories. with extended supersymmetry ranging from 4 up to 8. So the history of this, I believe, is that, of course, for n equals 2 in 3 dimensions, you can write down superspace and you can construct your superconformal, well, sorry, it's not conformal necessarily, your Chern-Simons theory, and you can choose whatever gauge group you like. It's fine. Now, I think this beautiful paper by Kim Young back when, showing that actually if you tune the gauge coupling to the Chern-Simons level, then you can enhance to n equals 3. And that was thought to be the maximum, but it turns out that you can go beyond. And how do you go beyond? What's the deal? And as I'll emphasize several times, the surprise here, how you go beyond, is that the choice of gauge group matters. Yeah? That's quite unique from a field theory perspective, that the amount of supersymmetry depends on the choice of gauge group, even in the classical Lagrangian. Okay. And the language for that is a so-called 3 algebra. And I'll give you a couple of definitions of 3 algebras and also why, in a way, they're nothing new. So for the purposes of this talk, a 3 algebra is simply a vector space V with a triple product. It's just taken to be a linear in each of its entries. And the idea is that given any triple product, this is the analog of an adjoint map, if you like, you can fix 2 elements, u and v, and then you get a map from v to v for fixed u and v. And the one requirement you want is that this triple product defines such a map, and this map is a derivation. And this gives rise to the so-called fundamental identity, that if this is phi, then phi ABC is, well, written there for you. Yeah? And this, if you expand this out, this gives you something called the fundamental identity. Now, since we're doing physics and we're thinking of the fields as being dynamical fields, matter fields, you're going to want some kind of positive definite inner product on this space. So, and this is actually crucial for the story. You have a positive definite inner product, and then this whole story induces an inner product on the space of derivations, if you like. So I've got a round inner product here for all things of this form. So these are endomorphisms, if you like, from V to V, or if you're just a bloke like me, V is a vector space, T and phi are matrices. This is the inner product of matrices is defined in terms, is consistent with, if you like, or defined by the inner product here. Okay. So there's a complex notion as well, which I put semicolons here, so that the last entry is always complex conjugated, and it's a similar story, V cross V into C. And again, you have a UV bar, and this is the analog of the adjoint map, and this must be a derivation. So it's a similar expansion. Okay? And this leads to a so-called fundamental identity. What the fundamental identity tells you, is sort of saying things backwards from what I said in the last transparency, is that the action of these phis on V is the action of a Lie algebra. So given a 3 algebra, you naturally generate a Lie algebra action on it, and I call that G. And it's generated by the choices of all possible phis, given by all possible choices of u and v. So turning that around, it just means that V is a representation of G, right? So you have a vector space, which is the representation space of some Lie algebra G. In other words, you've got a Lie algebra along with a preferred representation. That's what a 3 algebra gives you, but it turns out that this is an invertible map. This is the so-called Faulkner map. Given any representation of any Lie algebra, assuming you've got metrics on both the representation space and the Lie algebra space, then you can construct a triple product. You can sort of engineer the triple product from it by the so-called Faulkner map. So all this is really doing is a way of encoding information about a Lie group and a representation. Yeah? It's not some radical new structure. It's in fact the old structure just repackaged in a perhaps peculiar way. And I will mention this work of people who've classified it, in particular with regards to these M2 brain models. Okay, so of course, you don't have to think in terms of the three algebra language. You could just say, oh, well, it's ordinary gauge theory. Ordinary gauge theory, well, you've always got a gauge field. The gauge field is always in the adjoint. You have matter fields. The matter fields sit in some representation. That's gauge theory. And indeed, you can. Where I think and since this conference I think is meant to presumably be somewhat forward-looking, and where I think progress was made here was in the strange realization that, you see, as I said earlier, the amount of supersymmetry in things depends on the choice of the gauge group. And that in turn is encoded in the symmetry properties of the three algebra. So you want a three algebra with certain symmetry properties, and then you have to go back and ask what gives you that. And it turns out it's this rather peculiar list of field theories with their gauge groups. Yeah. So the other peculiar feature of these theories, and I'll review them in a little bit, in a few minutes. So first of all, is the gauge group depends on amount of supersymmetry depends on the gauge group. And the other funny thing about them from this sort of supersymmetry rulebook is that the gauge fields are related to the matter fields by supersymmetry. Yeah? So they're sort of in the multiplet, but they don't sit in the same representation. So that's sort of, if you take a normal book on supersymmetry, that's a violation. Now the difference, of course, is because you're in 3 dimensions, the on-shell condition is a flat condition. Well, no, sorry, not flat condition, but they don't have dynamical propagating degrees of freedom, the gauge fields. So this means that on shell, there are no gauge modes, and hence, it's not a contradiction with the statement that all the physical on-shell states should be in the same representation of supersymmetry. Okay, so let's go through the construction, hopefully not too lengthy. So for the first example, for n equals 8, you take V real, and you need this thing to be totally antisymmetric. This gives you n equals 8, 16 supersymmetries. So in most of this talk, mu nu is 0, 1, 2, and ij are the rest in 11 dimensions. So you can write down the supersymmetry variations. It's pretty standard stuff. These terms are standard. And of course, here this was just guessed because it's just conformal invariance. Just power counting tells you that you need something cubic in the x's here. And that's what we call the triple product. And then supersymmetry tells you it has to be antisymmetric because you want to contract with this one gamma. Okay, so there you go. You have an antisymmetric triple product on your space. And then when you close the algebra, you find, of course, it closes onto gauge transformations. So you have to have a gauge field. And if you have a gauge field, if you have gauge transformations, of course, these have to be Lie algebra transformations. So that tells you have to have the fundamental identity. And off you go. And you just write down the Lagrangian, and it's rather simple, right? Just kinetic terms for the scalars, the fermions. There's a sort of Yukawa type term, a potential, which is just the square of the cubic terms, and a Chern-Simons term, which can be written quite nicely in terms of this invariant inner product, the round inner product. Yeah. Now, of course, it was noted soon afterwards that positive definite choice of metric, there's just one finite dimensional solution. So you've got a 3 algebra, which is a 4-dimensional, it's R4. So you've got TA, A equals 1, 2, 3, 4. And the triple product is just given by the epsilon tensor and a coefficient here, which you later on realize k has to be integer. Well, so what is this? This is a triple product. This is how it works. You can easily see that the gauge algebra, if I just imagine soaking up these 2 indices, then and mapping on back on the algebra back on itself, I just get any antisymmetric matrix I like. So that's SO4. Right? And SO4 splits into SU2 plus SU2, self-dual and anti-self-dual. So you're looking at matrices MAB, and they're either self-dual or anti-self-dual. And so the inner product that you get is of the form, it's just T plus T minus and W plus W minus. This is one matrix and another matrix split into its self-dual and anti-self-dual parts. It's just this difference in the Chern-Simons levels, if you like. So when you put that into the Chern-Simons theory, you get the difference in levels. It's kind of curious. So what this says is that I've got a positive definite. This is a point made by Figueroa-Farrell. I've insisted on having a positive definite metric on the matter fields. The price I pay is that the metric on the gauge fields is no longer positive definite. It's a split metric. But you don't care, because then it's Chern-Simons theory. They're not propagating degrees of freedom. So you can make that sacrifice. You can go back and say, well, maybe I don't want to consider positive definite metrics on the 3 algebra, and then you get more choices. And they're classified by those guys. And they have a role, too, to play, the so-called Lorentzian 3 algebras, but I won't go into them at this stage. OK. Moving forward, another way to state this from a geometrical group theory point of view, of course, is that SO4 is SU2 plus SU2, and the fields are in the bifundamental. But, of course, the 2 bar doesn't matter because it's a real representation. So we have found ourselves in a Chern-Simons matter theory with SU2 plus SU2 as the Lie algebra. The Chern-Simons term is split with a minus sign, and this minus sign is actually important because that's also what allows you to have parity. So parity, since these terms are parity odd by themselves, when you flip them, you restore parity. Okay. And of course, that's the result that tells us the Chern-Simons theory that k has to be an integer. Okay. So moving on, you want more examples, you want more than one. I should point out at this stage, sorry to go back, that there are actually 2 families here. There's only one gauge algebra, but the gauge group can be SO4 or spin4. There's a global choice of gauge groups, so there's 2 families. And they have different interpretations, which I won't go into too much, but I will mention it later. But it's one of the lessons from all this is that everything's actually rather subtle, and it does matter what the global gauge group is. Okay, ABJM. How do you do it there? Well, you have a complex vector space, and you give up a little bit of supersymmetry, manifest supersymmetry. You get it back. So the xi's then get written in terms of complex scalar field Z. So there's 8 of them, but now there's 4 of these. Here's some mathy stuff. They're in 4 of SU4, and they have a U1 charge 1. And their dagger, of course, is in the 4 bar of SU4 and a U1 charge minus 1. And this is just notation. Dagger low is the index. Psi similarly splits into psi A in the 4 bar, and psi A dagger upstairs in the 4 charges. And the supersymmetries, well, you had 16, and they split into 2 plus 6, or sorry, times 2. Each one's 2 component. So n equals 8. This guy's complex, and an SU4 singlet, and this guy's antisymmetric with some reality condition. Blah, blah, blah. Just a bit of technical definitions, and then there you go. So you can write down the n equals 6 supersymmetry, and it just involves this triple product again, but now there's a complex entry. And the gauge is very similar in structure, of course. In fact, it's the identical structure, just written in complex notation. And you get the Yukawa terms and the potential. The potential is slightly uglier, but it sums up to the same thing. Okay, and the Chern-Simons term. So how do I get, the whole point of doing this was to get more examples. And what are they? And one class, there's another class, but one class of most interest is the so-called ABJM models. So you have m by n complex matrices, and you have, this is the invariant inner product, sorry, just a positive definite inner product. And you take the triple product just to be this. There is no natural product on m by n matrices, but there is a natural triple product given like so. So A, C dagger B minus B, C dagger A. And if you look at the gauge transformations, so those would be this derivation idea, where the variation, so the gauge action on ZA, you put it in the first slot and you fill the second and third slots with something arbitrary. Well, if you put that into here, so A is equal to Z, so you get C dagger B, that's N, and then on the other side, A is Z, so you get B C dagger, that's M. So you're just getting MZA minus ZAN, where these are these matrices. Okay, I've mixed up the notation a little. But this is, of course, this is the derivation acting on a scalar field. And you work out from this definition, the definition I gave earlier, the rounded brackets then are k over for the m by m matrices and minus k for the n by n matrices as the invariant inner product on the Lie algebra. So the gauge group is um times un, acting from the left and from the right, so the matters in the bifundamental. There's a slight technical point here, is that if you take m equals n, you actually only get sun times sun. Yeah? But you can add the u1 bit by hand. I'm going to perhaps return to this point later on. You can add the u1 gauge fields by hand, and that gives you ABJM. And by hand, the curious thing is that the gauge field associated to this u1 is in fact a supersymmetry singlet. Everything I've been telling you so far was looking at supersymmetry, how do I construct things out of supersymmetry, and I got what I got. And then when I go back and look at it, I actually have to add stuff in that's the supersymmetry singlet to get ABJM properly. Doesn't get, it's just delta. The gauge field for this has no variation under supersymmetry.
So that's consistent with the gauge algebra, the supersymmetry algebra that was on the show.
Yeah. Well, you can always do it, right? I can always take a field theory and have a field that just has supersymmetry or variation of that is zero. It's just.
Well, it has to obey the supersymmetry.
Oh, you wanted to close? Yes. So it is consistent with that. Yeah. Actually, we'll return to these points.
You can do the superspace formulation of just get what's on it. Oh, sure.
Yeah. Sorry. Yeah. If you're worried about closure, which you should be, then yeah, it requires it to be flat. Yes. Yeah.
So in 3 dimensions, there's a classification of supergravities. There may also be a classification of components. So can you take a decoupling limit for gravity in those constructions?
Yeah, I believe that's been done. Yes, indeed.
So all of those. So is there anything new that you get in this way? Or you get these ones and nothing else?
Well, obviously you're going to land on the same. Well, there's a list of superconformal field theories that sit here, and you land on that list. You can get more stuff that doesn't when it doesn't decouple, of course. So I'm not an expert in this particular story, but they start with the general 3D superconformal supergravities, and then they have this so-called embedding tensor approach, and there's certain special properties that are required for the decoupling limit of this embedding tensor, and that lands you on this list, I believe. But I could be mistaken. Or slightly, some variation of that statement is true.
And another thing which is related is, as you say, I mean, the Chern-Simons terms are, well, the Chern-Simons terms are non-dynamic, so you can totalize them as scalars.
Well, not.
In 3 dimensions, so in 3 dimensions, basically on shell is the same as a scalar. You have epsilon, u, rho.
Well, it's of a zero scalar, right? Because the on-shell condition here is it's flat. Yeah.
There are some dualities with Chern-Simons, but they're very subtle.
Yeah.
Particularly not really.
Oh.
Oh, I see. Okay, but that's not what happens with supergravity. Okay, so
No.
Supergravity theory.
Yeah. So just so you get this list here. And of course, if you take SU2 times SU2, you get the BLG back, just in complex notation. And the list continues. You can give up a little bit more supersymmetry, and actually there's another example with n equals 12, and I forgot the gauge group because it's a little odd. It's like SO2 times UN or something. What? Sorry, it's got 12, so it's n equals 6. There's 2 with n equals 6, 2 families, ABJA, and then another one with the gauge group is like UN times SO2. Yeah? SPN. Sorry.
SPN times O1.
Yeah.
But the n equal 4 case, you do not generalize. You still have this special feature for n equal 4.
Yes, yes. So then it turns out that it's a superalgebra. This is the Gaeta-Witten story.
It's funny because there are offshore
in 3 dimensions. So, right, but that's of Yang-Mills, not of Chen. So I got, so there's a nice list, and the symmetry properties, the amount of supersymmetry, and again I emphasize this is the amount of supersymmetry of the Lagrangian, is given in terms of the symmetry properties of the structure constants, basically, this triple product. And the actions are entirely built out of the triple product, just like a Yang-Mills theory, n equals 4 is built out of FABC. So the Lagrangians are, essentially the Lagrangians are all the same for all of these theories. It's just a question of what you input to these. And so I'll reiterate some points. I sort of already said this. So some of the novelties, I mean, why weren't these theories discovered in 1972 or 76 or whenever it was? And the answer, I reiterate these points, is the gauge fields and matter fields are in the same sort of quote, it should be quote multiplet, but not in the same representation of the gauge group. And the amount of supersymmetry is determined by the gauge group. The Lagrangians are more or less the same. And the 3 algebra was useful because it's a way of emphasizing or highlighting what the supersymmetry is, and then you find out what the gauge group is after the fact. Yeah? And then I got this high-tech diagram, the triality of the triple product. But here are the examples, and here's the rather obscure list of gauge groups that you require, right? So maximal supersymmetry is SU2 plus SU2, and then you've got SUN plus UM, or SPN plus U1 for n equals 6, and at n equals 5 you get these groups, including G2 plus SU2. So, I mean, who ordered that? It's one more item? I missed it. Oh, where does that go? N equals 5? Oh, I apologize. Was it? But okay, maybe this is not even the full list. I apologize. But the question is really who? I mean, this is sort of bizarre, right? I mean, this is the answer. This is the gauge groups, right? I mean, it's not whatever gauge group you like. The gauge group you pick up later. Yeah.
I mean, are they completely decoupled? What role do they play?
Ask me at the next after a few transparencies. Okay. They're subtle, but yeah, they can be integrated out. Yeah. Okay. Of course, so the gauge group is really important here. I mean, it would be wonderful because, of course, we're going to come back and we'll talk about M5 in 20 minutes. And, of course, M5 are also, it's only expected to work for certain gauge group choices. So perhaps this, well, this is pure not even speculation. This is just a wish list that somehow we need to know more about what gauge groups mean for gauge theories and what subtleties depend on the choice of gauge group, because we're used to normally thinking of all gauge groups at the classical level being the same. Of course, quantum mechanically, we've always known there's important differences. But that's a classical list.
Discuss what the meaning of the gauge group is
from the 11-dimensional perspective. I don't know. I wasn't going to. I mean, I don't know. You see, I mean, it's kind of strange because let's go back to, forget even 11 dimensions. This is the IR fixed point of SU2's maximal super Yang-Mills. And the gauge group is in some sense enhanced to SU2 times SU2. And in fact, this is the general SUN, or sorry, UN, it should be UN.
I thought it was meant to be the nature of the singularity in the orbital.
I'm not aware of that, but that you can. The 6D models. Yeah, well, it's related to this embedding tensor approach, which, if Henning was here, he would tell us. Yeah. Yes, exactly. So groups like this, I don't know if it's exactly the same list, this definitely appears in supergravity. And there it relates to the so-called embedding tensor, because this 4-index object is basically an embedding tensor. It's telling you how you can embed one gauge group into another.
In fact, there's other groups, but then I guess these are the ones that remain once you do this, when you look at it.
Yeah, it's a small, this set is a smaller subset than the 3D supergravities. Okay. So that was sort of the review. The next thing I wanted to tell you now is the essential dynamics of these systems. And this is sort of, so lesson 1 was like, be open-minded, the gauge group matters, it's magic things can happen. But that was all classical. That was a classical Lagrangian. Now we want to examine the actual theory itself that you get out of that. I mean, why do we think that a UN plus UM Chern-Simons theory describes n M2 branes? Yeah? Why does this describe 2 M2 branes? This is slightly more easier to buy. What are the actual physics? And a big question would be like, well, where's the center of mass multiplet?
That was not my question. Do you have an interpretation in terms of how many M2 branes for all of these cases?
Oh, yes, yeah. So I believe so. So these do indeed correspond. So this one is the standard case, meaning it's just n M2 branes in a ZK orbifold of 11 dimensions. Here you have an orbifold, an O3 plane, oriented fold, excuse me. And then here too, there's oriented fold stories, I believe. Yeah. And you can use some, as it's called, de-brainology to sort of see how you got those gauge groups. It's in the ABGM paper. Where am I going? Backwards. Okay. So the first question you might ask yourself is, well, if these are M2 branes in 11 dimensions, where's the center of mass molar? I would expect a brane system embedded into flat space to have, and this is, of course, now everyone knows it's not flat space, but it wasn't known at the time. Where's the translation? It's the most simplest thing I can ever do for a brane is to pick it up and move it over there, right? And that's usually described by a free multiplet. But these models don't have any free multiplets in them. So what do we think we're looking at? So let's go through a little story. So this section gets technically detailed. Those who are experts have seen it many times, and those who aren't won't learn anything from my presentation about it. So I apologize to both of you. I'm going to rush through it a little bit so that I can talk about crazy stuff afterwards. Okay. So let's restrict to ABJM. So the first thing we want to do if we want to understand the physics of a system would be to say you look at the vacuum moduli space. That's the set of zero energy configurations for these M2 branes. So it turns out that you have to set this triple product to 0. Even that's not obvious, by the way, because of the form of the potential, but it's a little bit of work to see that generically this certainly implies that the massless and this is obvious that you have to set it to 0, but this means that the ZAs are commuting matrices is not obvious. And in fact, they don't have to be all the time, but for generic points in the moduli space, that's the case. So just like D-branes, I have the ZAs have been diagonalized to Z1A to ZNA. Okay. And then we follow the usual rules that we would do for D-branes, is we say, well, we want to identify fields that differ by gauge transformations. But the gauge transformations are bigger now. It's G left and G right. Well, the first thing you might look at is G left equals G right. That's just an adjoint action. So I'm doing UN times UN. And so that's similar to D-branes, and that allows us to put the ZAs in diagonal form, which I've already done. And also, it gives you that you can flip the ZAs. Yeah? You just take, for example, this. So just like D-branes, I've got diagonal matrices, and the individual eigenvalues can be permuted. But unlike D-branes, there's a continuous transformation. I can rotate them by a phase. So for example, I could take G left equal to G right inverse, and that'll do this for me. So we have to worry about this now in the moduli space, and this is where it gets a little bit detailed. Okay. So the way to do that is you restrict to all the fields to the moduli space, and let's look at the Lagrangian. Okay, this is where I have to apologize. It's a bit messy, but it's just, first of all, I'm just summing over all these eigenvalues. So we could look at each one independently. Don't worry about the I-index then. Just forget the I-index and look at any given eigenvalue. So there's a covariant derivative on a ZA, then there's the Chern-Simons terms, and that's all that's really here. Yeah, everything's just diagonal, so you can just think of each individual component. This relates now to the U1s that Martin was worrying about. So the ZA is only coupled to the difference of the left and right gauge field and not to their sum. So you introduce a B and a Q. And the gauge field is just the gauge covariant derivative is just involving the B, and then you get this B wedge F type interaction, B wedge DQ, for the Chern-Simons term. And it's helpful to dualize that Q so you write its field strength as H, and then you put a sigma to impose DH equals 0. You do your typical thing, and then you can integrate out H. And this tells us that B is flat. This is this U1 hanging around. Okay, and with a 1 over K here. So everything gets mapped to pure gauge. The Lagrangian on the moduli space is then just d mu WA, where WA is e to the I sigma over K times Z. So you've just found some gauge invariant coordinates on the moduli space. Okay? Fine. Next thing you have to realize is that sigma is periodic. Where was it? It was written here as integral Lagrangian of sigma dH. And this is where things get a little subtle. Sigma is periodic because of a flux quantization condition. So the difference in the action of sigma and sigma plus 2 pi is a dH term, integral of dH. Now, not wanting to go through too many details, dH is the sum of a d F left and F right. Each one satisfies a 2 pi periodicity condition. And there's another condition I didn't write, which is that they're equal. So they're both 2 pi and equal. So this sum is in 2 pi because it's a half. Now, note here that this is quite subtle. This is where the choice of the gauge group really matters. If it's UN, SUN, or SUN mod ZN, you will get different answers for these periodicities. And hence, sigma will have different periodicities, and what happens in the next page will be different. But let's stick to the standard choice. But it really is relying here on how you quantize the fluxes in the theory. So now we had these coordinates on the moduli space, but they're subject to this identification. And here's how you see that there is actually an orbifold action in space-time. That your R8 is better thought of as a C4, and then there's a ZK, which is coming from these residual gauge transformations. And so the vacuum moduli space, all told, is a symmetric product, n copies of C4 mod ZK. And hence you raise your hand and you say, aha, I've got n M2 in C4 mod ZK transverse space. And indeed, you can go look at this orbifold, C4 mod ZK, and you realize that it in fact serves, there should be 3/4, not 1/4. It breaks to 1/4 and preserves 3/4 supersymmetry. And that explains why you got n equals 12 supersymmetries. And also it explains why, for generic K, you couldn't identify a transverse center of mass mode because everything's going to be stuck at the origin. Except at K equals 1, it should be there. Right? K equals 1, there is no orbifold. This describes flat M2's in flat 11-dimensional space-time. Where's the center of mass? Well, let's go back. So now we want to be a little bit more sophisticated. We say, oh, because the moduli space is very simple. It's just the abelian part. It's all very nice. But what's happening, the full theory exists, not just on the moduli space. So what happens there? Well, let's say I want to start probing 11 dimensions. I'm claiming this thing sits inside 11 dimensions. So let me turn on some physics. Let me start moving around in 11 dimensions. How do I do that? So here's my diagonal element. This would describe the M-Branes sitting at some point ZA in the transverse space, if I want to just give them a little bit of a spin, kick them up around the 11th dimension, I can do that. I can just give them a phase factor here, e to the I omega t. So now they're spinning around this 11th dimension. But they're not, because that's pure gauge. All right, so that's not how you turn on an M2 brane and make it spin in the extra dimension. So we have to think a little deeper. So it's helpful at this stage to go to the Hamiltonian. Yeah? So we forget the fermions now and just look at the Hamiltonian. So sort of standard stuff from the first line, and then you get the stuff coming from the Chern-Simons. And of course, these are the coefficient A0, so these are the Gauss law constraints, right? Because A0 will not have a conjugate momentum. So you get a Gauss law constraint that says that the fluxes are given by these combinations of positions and momenta, and if I expand out my guys in this way, so radially, so each little z now comes a radius direction times e to the I theta, then this constraint is like this. So kicking these guys around the circle of the extra dimension is turning on magnetic flux. Yeah. And that's actually not too surprising, because in the old days, if you wanted to do the abelian M2 to the D2, you would simply have taken the scalar field and you would have dualized it. And if you dualize the scalar field, naively its momentum is indeed just the magnetic flux. So it's still the same old sort of story, that the momentum around the 11th dimension is a magnetic flux. But now I'm in the full theory now. I'm not just on the vacuum moduli space, and I want to know, like, how am I going to compute operators and things that correspond to really moving and really doing dynamics in 11 dimensions? And you realize that this is this U1 charge that's being interpreted as 11th dimensional circle momentum, but it's gauged, so operators can't carry it. So if you look at some expansion of operators, you'd have to put a trace here, excuse me, to get a gauge invariant observable, but you have to string them between complex and complex conjugate, field, complex conjugate, or something like that. So in order for the U1 charges to cancel out. A more naive way to think about it is an ABJM, and typically this is an N by M matrix, so it has to be followed by an M by N matrix. So it's got to be Z, Z dagger, Z, Z dagger, Z, Z dagger. This, not gauge invariant, not allowed, carries U1 charges, and it cannot compute, it's not a gauge invariant observable in the field theory. So if you restrict yourself to only these objects, you're never really going to see the 11th dimension. You're not seeing anything which carries a U1 charge, anything that carries a KK charge. Well, KK, it's not compact, but it's, it's the charge around that U1. But of course, this is a known problem, and it's known how to solve it. You have to have monopole operators or Toft operators. So you want to create states that carry magnetic charge, and it's done like this. So it's not done by having some operator, which is a polynomial or some function of the fields that you put into the Lagrangian. It's a prescription for how you deal with the path integral. So you declare a monopole operator to be at the point y, to be a prescription on the boundary conditions of the path integral of the normal action with the normal operator insertion here. And the prescription is that near the point y, you encircle y by a two-sphere. You're in the Euclidean section of the three-dimensional path integral. So a point is surrounded by a two-sphere, and then you can declare that that two-sphere has a certain flux on it, a magnetic flux, 2 pi qm. Right? This basically says that around that point, the fields look like Dirac monopoles, of this type. And in general, our qm will be in un times um. It's a magnetic flux, and it's subject to standard Dirac quantization condition. So again, I'm going to skip through some things because either you know it, or it's going to be too fast anyway. It's discussed in various reviews. I have a review, but because of the Chern-Simons terms, the monopole operators are not gauge invariant. So if you do a gauge transformation, because of the singularity, and you pop that into that prescription here, you will see that M transforms by a phase factor. And it's a little long story, so you find out that the monopole operators sit in multiplets, and they sit in multiplets under the gauge group whose highest weight is given by K, because there's a K that comes out from everything because of the Chern-Simons terms, where this is given by the magnetic charge vector. So this is this GK, not GKO, God, I can't, GNO, excuse me, the GNO construction of monopoles that they sit in gauge theories, that they tend to sit in representations given by highest weights, given by their magnetic charges, and here it's multiplied by K. Okay. All right, so this is a very abstract definition of a monopole operator, and the fact that they sit in these representations. And it's also rather difficult to compute with. So I want to just give you an example to show you that we've already had the monopole operators. We had them back when we were discussing the moduli space. Yeah. When we wrote down something like that, at one point we had the Lagrangian of this form. Well, I claim that the monopole operator is just e to the I sigma, where this is the dual photon, if you like. Because if in this form of the Lagrangian, if I stick it in here, I can replace it with exponentiate it by putting a delta function, but that delta function is just shifting dH to dH plus delta, and that's inserting a magnetic charge at x equals y. So the gauge invariant operator on the moduli space, W, is in fact a monopole operator acting on Z. So we've already seen it. And these guys are important. In particular, if you look at k equals 1, the translational modes, what happened? Well, this is the normal translational current anyway. The conserved current you'd normally write down would be trace d mu Za. That's the conserved current whose conserved charge you would think is the motion in the x mu direction. Sorry, in the Za direction. But it's not gauge invariant. But you can dress it with a monopole operator, and you get something that is gauge invariant. But this monopole operator only exists because it only has the right charges at k equals 1. Otherwise, it's got too many charges. See, the minimal charge of the minimal U1 charge of a monopole operator is k. And this guy has got charge 1, so you need k minus 1, actually, to cancel it off. And this is also how the supersymmetries arise. So they are there in these theories, but they are not there in the Lagrangian of the theory. Yeah? Okay. And then a quick slide on how PLG slits in, which is just out of curiosity, because it's kind of a curious story, developed over various papers. It's usually only ever describing two M2's, although recently it was shown by these authors that at k equals 3, it describes the interacting part of 3 M2's. Then you can just add in the center of mass for free as an extra U1 multiplet. In these other theories, when the center of mass exists, it exists because of the monopole operators, not because of the fields in the Lagrangian. Okay. I was thrilled by this paper, by the way, because it came out maybe almost a year ago now. When we first did the M2 my first guess, because I had no idea what was going on, was that it described 3 M2's, because I had 8 components. Sorry, I had 8 plus 8 fields for motion in R8, and I thought, well, and they're interacting, so that's the center. That's everything minus the center of mass. I was completely naive. I had no idea what I was doing. And later on, when we realized all this stuff about how this moduli space works, I felt like such a fool for having published this claim in a paper with 500 citations, which nobody ever read. And actually, I was right. But it was just complete luck. Well, right in quotes. All right. So that's the story. Some lessons and a question. It's still too much to ask for all the symmetries to be manifest. Huh? None of those models have all the symmetries you want in the Lagrangian. It was helpful, I think, to think about just 2 M2's, because that seemed to allow for more symmetries to be manifest. The quantum theory is very different from the classical one. Right? If you just looked at only the classical theory, you'd be wrong. And in particular, the corollary to this third point is the fourth point is you have to look at quantum operators to see the full physics. At the end of the day, when you're looking at M-Branes in flat space, you are talking about a strongly coupled system. It's a purely quantum strongly coupled system. Even if I give you a Lagrangian, it's like trying to find protons out of the QCD Lagrangian. It's not going to be there in any obvious way. The role of the gauge group is non-trivial, and global choices really do matter. If I'd taken SUN times SUN or SUN mod Zn for those theories, I would have got different periodicity, and I would have produced a different moduli space, and the interpretation would be different. And that would extend to the full theory about what monopole operators. So the choice of global gauge group determines what monopole operators are available to you. And if you change the gauge group, you will change. In particular, you will remove monopoles from the theory. And my last little question is BLG is still kind of interesting to me because for large K, it's an infinite family or two infinite families of 3D superconformal field theories, which look like they want to belong to M theory, but apparently they don't. The only indication is that if you mod out by ZK, you get ABJM. So it's like it's slightly higher than M theory. You have to mod out to get the M theory answer. Okay, let's all do the seventh inning stretch. Any questions on M2-Branes?
Suppose I set n equals 1 DBJ, and I want to describe 1.
Yeah, n equals 1. Yeah.
1 into grid. So is it understood how it's related to, for example, the liquid operating action?
Well, n equals 1, this is a free decoupled limit, so it's just a free theory. So yeah, you can, it's just the free theory written in complex notation. And then you gauge a phase. So,
I mean, I'm asking, there's a matrix model for the membrane, or, the discretization of that action, the VST action, or the liquid action. So the question is, suppose you put n equals 1 in all of these forms.
yeah.
And can you do something and get your
Yeah, so this is just the free IR limit of those theories. So it's just a free theory. Whereas those M2-Branes were M2-Branes coupled to the background supergravity fields, right? Including all the alpha prime, what do you want to call it, M-Planck corrections and things. So this is just the tree level IR of that. So it's very not interesting from that point.
Well, still, there should be some way of getting that from.
You can go from theirs to this, yes. You take theirs and you just go to the IR limit. So you throw away all the interesting terms and you're just left with the free theory. And yeah, ABJM at n equals 1 is a free theory. Yes. Okay. So let's put on the boxing gloves and let's talk about the M5 brane, okay? So M5-Branes and 2,0 theory. So now we have another prediction, but this one's really striking from M theory, right? This is you go at the LHC and you say, I want to look for 6-dimensional field theories. So the decoupling limit of NM5-Branes leads to a superconformal field theory in 5+1 dimensions. So this is striking because I don't know any scientist who knows how to handle a quantum field theory above 4 dimensions. There's no textbook, and there are no basic rules that tells you how it works without having to embed it in string theory and do all that, whereas you shouldn't have to. Okay, so I find it's a striking claim that we should all be interested in because it has impact outside our subject. Okay, so the abelian cases have been well known for years, and again, what's difficult about these papers is the coupling, the full type DBI type action to all the supergravity fields. At the IR limit, they're just free theories. So you have 5 scalars now. So now I is 6, 7, 8, 9, 10, and mu is not 1, 2, 3, 4, 5. You have scalar fields, which are free. You have a closed 3 form, which is self-dual, and you got some fermions. But for more than one, you get an interacting theory known as the AN, or actually probably AN minus 1, 2,0 theory. Intuitively, one has this picture in mind of M2 branes and M5 branes. So the M5's are the blue thingies, and M2's can end on them. So one likes to think of these as the analogs of open strings on D branes. They're certainly the natural BPS states on the M5 brane theory. And rather than having Wilson lines, you might think of Wilson surfaces. So we did the abelian case long ago as a nice 1 over R squared, but people like Christian have been spending a lot of effort trying to think about how the non-abelian theory would work for these things, because that's some kind of curious version of the norm transform. And then there's one other thing that ADS-CFT, I said I wasn't going to talk about it, but here's one more reference to it, is it tells us that the number of quote-unquote degrees of freedom of n of them scales like n cubed. So that's rather dramatic. And no one has a clear picture of that, I think, even hand-waving. There are some nice hand-waving, actually. But concretely, no. Okay, so what do we do with this theory? Well, the first thing we do is we put it on S1, because that's what we know how to do. So then you get, the standard relation is, of course, you get D4 branes, and this is the string coupling constant. And so this is described by UN 5-dimensional Super-Yang-Mills theory with this coupling constant. And so you actually realize that the 2,0 theory has a beautiful role as the UV completion of 5-dimensional Super-Yang-Mills. And what's happened is there's been an enhanced Lorentz symmetry. Before there was an enhanced R symmetry, and now there's an enhanced Lorentz symmetry. So that's also quite an interesting thing. So SO14 has gone to SO15. And so again, this is another prediction, if you like, that actually there are good quantum field theories in 5 dimensions, and of course there's a much bigger story than I'm telling you here, but in this particular case, in the UV, they run to 6-dimensional theories, and their Lorentz group enhances to SO15. It's been pointed out long ago that at least at some level, the Clausius-Klein momentum of this extra circle are handled by instanton solitons, meaning that you have a 4-dimensional spatial sections, and the instanton number on that spatial section plays the role of the momentum, and they're associated with this topological current. Okay. Well, if you can do one circle, you can do 2 circles. Of course, you can't really do the first circle, but have got the first one, let's do the second one. So you've reduced again a second S1 of radius R4. So there you get 4D Super-Yang-Mills, and coupling now is going to be 2 pi R5 over R4. So it's this ratio that is the interesting feature. S-duality, this is the classic Monton-Olive duality, swaps perturbative modes and monopoles, and it swaps R5 with R4. It's just inverting G to 1 over G. From the M5 point of view, this is just a diffeomorphism in 6D. It's a large diffeomorphism of the 2 torus. And if, the big if I gave you a nice diffeomorphism invariant expression for the M5 brane, this would be manifest. It would have to be. But that's the big if. So the next point, of course, is that Monton-Olive duality only works for ADE gauge groups. So the 2,0 theory should only exist for ADE gauge groups. And it was first originally actually identified not through M theory, but just through string theory type 2b at an ADE singularity of K3. Okay, so no action. So there's many claims, people put their names to it, that there's no action for this theory. So let's just go through some of them. Let's not worry about self-duality. Let's just think, what the heck could it be? At the end of the day, it's physics, it's got to be made of fields. What do I put? Well, I've got this 3-form, h squared, I've got the scalars, I've got my fermions, of course, but what do I write for interactions? These things here are renormalizable. There's no coupling. The coupling constant's dimensionless, but they're unbounded. There's not going to be a vacuum if I have this. And then you have to add anything else that's going to be non-normalizable. There's going to have to be some mass scale in here. Well, that's, by definition, not what you're interested in. So, Well, you'd have to give me a prescription for what happens when it goes to 0.
Yeah, okay, the 0 point is a half. But it's still, it would
I mean, well, not necessarily. I mean, how would you actually do that? I mean, what are the effects that you get near the boundary? That's,
one collider of superconfirm filtering has tensor moment KT, and you have that kind of coupling in the
yes.
That's perfectly fine. When you x goes to 0, it's this conform filtering.
Yeah. So you can expand around. Okay. So let me expand this. You can fix x at some point. Expand around some point x, which is not the origin. Perhaps let's say there is no x cubed. That'll help. So there's no potential. So you can expand around x at some finite value, and people do this. And certainly as an effective field theory, one could expect that you could do this, right? And as long as you don't probe, if you do an expansion around x equals 1, small expansion, you'll be okay. But since you're supposed to be defining a superconformal field theory here, I think you have to say, what's preventing it from going down to x negative? Because that you will lower the energy.
Well, I mean, the scale of field parameters the distance of the type, right? And if you say, okay, it doesn't matter how the distance is,
these are words.
No.
We are scientists.
No, the fact that distance of parameters the distance of the type, that's not words. That's what we see in theory, right? That you can see in many forms. But
well,
there's a theory that doesn't care about
but what? This is very schematic. So now I ask you a question. But that x lives in the gauge group.
Well, no. I mean, in our model, for example, that's fine.
But you're gonna. It's not fine, right? You're gonna have problems.
No. That point is fine. That point is not the issue. There's not the issue.
Which point? Sorry.
This point that this is unbounded because we just say.
No, this theory does not have a vacuum, as understood. I can lower the energy of this theory. And you're going to have to you have to give me some real answer. Why not? X is only positive, but then I need to know you're going to oppose that by Lagrange multiplier, or what? I mean, what are the physics near x equals 0? It's how you can't just declare it because it's physics. It's physics.
Well, no, but I mean,
the system at x equals epsilon can lower itself by going to negative epsilon. What's going to stop that?
You have to parameterize where you feel slit mathematically, right? So you have to say what it is.
But then the metric would be different in the path integral.
It has to be the real line, right? We don't extend the context.
Okay. All these things are unleashing a Pandora's box of issues, which you have to deal with. So, no, you could say x is only positive, but then I would worry, well, what are you putting in for the measure of the fields? For the measure in the path integral of the fields. Is x equals 0 infinitely far, or is it? These are all issues that must be discussed. They can't be swept under the rug. That's my point. I will come back to this because, of course, I'm guilty of this too, by the way. I'm guilty of this. I've written papers where I ignore this, and I say, that's fine, and I'm okay with that. But, so we all have our sins. Well, not Kim Young, he's an angel. Let he who amongst you is without sin be the first to cast the stone. Okay. So, how can I obtain this curious 4D Super-Yang-Mills thing, which is that the action goes like R4 over R5 from a 6D action, which would scale like R4 times R5. It's a very simple observation. Now, you can imagine tricks around it, but yeah, that's curious, right? And in fact, the fact that R5 appears in the numerator, sorry, this is the denominator. The fact that R5 appears in the denominator here is highly non-trivial, and it's used later. So then there's another argument from Witten, which is let's take our theory on a 4-manifold times R11. Then you get B2 plus chiral bosons and B2 minus anti-chiral bosons. But it's known that there's no modular invariant partition function unless this difference is 8z. Now, since I gave this talk in August, I realized there's actually a theorem that says this is always 16z. So you're fine, right? This is actually always 16z. And in fact, it's almost the other way around, that if you could give me the 2, 0 Lagrangian, I could prove this Rollins theorem straight off the bat, because it tells me that when I reduce on a manifold, I would have to have a multiple of 8. Well, actually, you get a multiple of 16, but okay. It's at least consistent with the theorem. But this is just the abelian theory, yeah. Yeah. So this slide was, the previous slide was talking about an interacting theory and not worrying about self-duality. This slide is worrying about, this is in the interacting theory, this is worrying about, well, this is a generic one. This is worrying about just the abelian theory itself. Yeah. Well, so here's the line. CP2 can arise. So this is Witten's objection. Of course, Witten surely knew about Roland's theorem because he doesn't mention this. This was my interpretation. He says CP2. CP2 exists as a solution in M theory. So, and CPT has got this sigma of 1. Sigma is the difference. It's got one chiral mode. So the M5 brane on CP2 doesn't have a Lagrangian.
I'm a little bit puzzled by the next line. There.
Which one?
I realize it's skipping ahead, but I mean,
this one?
The 2-0 theory, even the abelian one, definitely has a gravitational anomaly, right? So the quantum theory is not diffeomorphism invariant. So why would we even expect a classical Lagrangian, which was?
Well,
oh, it's fine, but just as a purely six-dimensional theory, I mean, I know that it has a gravitational anomaly, so why would I be looking for something which was diffeomorphism?
well, I should add that to the list, actually.
Well, okay.
I agree. Yeah, so we do not expect. I don't have that one now. So this one is the Tashikawa test, which is the 2,0 theory exists for ADE, but if you compactify in a circle with twisted boundary conditions, you can get BC gauge groups. So then you might take SU2n,
Or G, right?
yeah, no, and give it, and then you should get SO2n plus 1. But this is not a subgroup of this. So what kind of Lagrangian is going to do that for you? It's another cutesy one, like cutesy. I mean, I don't mean that derogatively. This one is a very cute thing to state. Oh, how the hell do you get R5 in the denominator? And here it's how would you get, SO5 from SU10? And actually, there was a paper recently, since August, where they just note that the 2,0 superconfirm algebra does not admit conserved currents whose dimension approaches that of a free theory. And this would rule out even a discrete weak coupling limit. So like the M2 brane models, there's no continuous parameter, but there was a discrete parameter, which got you to weak coupling. And this claim is that there's not even a discrete limit to weak coupling. And then I could put Jack's objection on too, actually. Yeah. Yes. Yeah. Very good. So for small n, this isn't a problem. It's only a problem for large n. Did I? Yeah, I meant the next one up. Sorry. I'm jet lagged. I'll get that wrong without being jet lagged. Yeah. No, it's true. And actually, my favorite example is always SU2. And SU2, it's even SSO3 and SU2. No problem. And actually, I'll come back to that if you indulge me later on with some truly things. Okay, so let's talk about some constructions of this theory. So, and this is in historical order and my own prejudices. But so there's the DLCQ, which was the first one, where you consider a null compactification. And a null compactification should be viewed as the limit of a space-like compactification. And in that, you see that the null radius, R minus, is R5 over epsilon, where epsilon is going to 0. But this is the key point that makes this whole thing work. If you did this for a normal field theory, this would be junk. But for the M5 brane, it works. Because to keep R minus finite, you must shrink R5. And hence, the 2,0 theory is well described by 5D super Yang-Mills. So actually, in this DLCQ limit, you land on five-dimensional super Yang-Mills, it squashes you onto it. And the result is that this description becomes sort of exact, where the momentum is the instanton number, and so the dynamics is reduced to quantum mechanics on the moduli space of SU, and it should be UN instantons with instanton number K. And K is the momentum in this null direction. Sorry. Here, there. Okay. So it relies heavily on this fact, this miraculous fact that this R5 goes in the bottom when you go down to 5 dimensions. The next construction was deconstruction. And this one really came out of a bunch of phenomenologists and a bunch of string theorists. So you construct a quiver diagram, I think they called it a moose, that results from this brane diagram. So since we're a brainy audience, I put this way. So you have D4 branes this way, and it's identified. This line is identified with this line. So the left and right hand is identified. It's a circle. So the D4 branes are described by SU. Unfortunately, I ripped this off from one of my colleagues' papers, Costas and group, and they have K and N the other way around. So it's SUK to the N super Yang-Mills, and there's 2 K flavors, because from each side you get one. So in the bifundamental of each SUK. So this gives a 4D N equals 2 superconformal field theory, because you've got the NF equals 2K business. And then you need to go on the Higgs branch, and you break that down to SUK, this would be K. And you can tune it in such a way that apparently, I mean, of course, it's all very technical, detailed. You tune it in such a way that you get a well-defined limit as you take the number of nodes to infinity. So it's like it has a KK tower, but it's cut off at finite n, and then it grows it back up as n goes to infinity. But because it's an n equals 2 superconformal field theory, it has an S duality. And so in addition to sort of like the W boson KK tower from boson, branes that connect missing 1, missing 2, missing 3 branes, you'll get an S dual of them, of monopoles, so you'll get an SL2 multiplet of towers, and you reconstruct a 6D theory with SO5R symmetry. And these are the people who I stole the diagram from. And this approach has sort of languished until this paper, where actually they were able to use it to successfully make exact localization calculations. Okay. So here's my hat in the ring, along with Douglas and my collaborators. Well, I go back to this list here, and we've discussed what we do with this. So let me discuss throwing out this, but keeping this, in some sense. So we propose that actually where are we going? Here we are. That 5D super Yang-Mills is somehow non-perturbatively well-defined. And at finite G, you can use it in principle, if you were infinitely powerful computer-wise, to compute things, and you would find you would find the 2,0. There's no difference between 2,0 and this. The reason is you get a complete KK tower of soliton states in this theory. So, if you're going to add a UV completion, you have to take out that Kruger-Klein tower of soliton states and replace it with microscopic fields.
I'm not sure whether this is exactly the right moment to check, but there are other UV completions of the 5D maximally supersymmetric Yang-Mills. For instance, it could arise at the low energy limit of a 1,1 theory in 6 dimensions. 1,1 super. Wait, let me say. That itself is not UV complete, but is UV completed in type 2A string theory.
It's got SO4R symmetry.
Which gets enhanced in the infrared in the same way that
but this isn't a fixed point. This is off a fixed point. So.
No, I'm saying that, that there are various. So if you want it UV completed as a field theory, then the 2,0 theory is your unique answer.
Yes, that's.
If you want it UV completed in string theory, then you have other options. But as a as a 5-dimensional physicist, how do I know which UV completion I'm supposed to be aiming for?
Well,
in other words, if I just have the 5D super Yang-Mills theory, I can imagine you'd be completing it in several
So
different
our
ways.
claim is that and I totally agree that this claim is contentious, right?
Okay.
Totally agree.
So I'm happy to make that interjection later if you,
Yeah.
if you want to.
But
Minimal, yes,
Yeah.
I agree with you. If you want a unique complete as a field theory, then the 2-0 theory is your answer.
so my claim is that God is sitting up there,
Right?
and he knows they're the same because he sees he can somehow completely solve the path integral, and it's a done deal.
God, my God believes the same thing. So.
But I don't think you could do it with the 1,1 like you suggested. But that's also,
No, there's 1,1 that's small. No, 1,1 didn't split the animals together. Why?
Oh, why, for instance, I mean that, but not as a field theory, but as a, so 1,1 little.
I want to complete it in a field theory.
6-dimensional UV completion of this theory.
I should do that. That loves to also play game. So he can play this game.
Okay. Right. Well, we had a prescription that the analog in this case of the monopole operators, which were so crucial in the three-dimensional case, the M2 case, are replaced by so-called instanton operators, where you can imagine what that is. You have a five-dimensional theory, and you have to take out a point, and you surround it by a force sphere, and you declare that there's instanton number on that force sphere. And the wish in here, of course, is that if we're going to resolve the obvious, this is perturbatively divergent, you'd need some miracle, and the idea is it comes from small instanton-soliton effects, where the size goes shrinking to 0. But people have been able to see n cubed, at least using the gauge theory alone, which of course is not evidence, but it's still striking. Okay. Given that I'm running out of time, I'll just skip that slide. Okay. Just make a point that actually these three things I've just mentioned for you are all kind of related. So here's something I'll say out of provocation. The DLCQ description. Now, I never get my head around DLCQ. I fully admit that. I've never quite understood it conceptually. But it's rather remarkable to me because it's very crystal clear, the argument. The 2,0 theory must also give, so the DLCQ description of 2,0 theory gives the UV completion of 5D super Young-Mills, because it's giving the 2,0 theory. But the only information you put is what happens in the IR of Yang-Mills theory when expanded around a soliton background. So how does it know, right? Like, if the only information going into the DLCQ of the 2,0 is the IR physics of 5D super Yang-Mills, and yet that's supposed to define the UV of 5D super Yang-Mills, that's suspicious. Unless, of course, the UV is contained in the IR, or at least the physics is the same. Of course, there's a big caveat with DLCQ, I should point out, which is the instant moduli space has singularities, and you'd need to know how to deal with them, and therein could lie a lot of difficulties. Another point of view is that the action, if you do deconstruction, it deconstructs an action. What action does it deconstruct? It deconstructs 5D super Yang-Mills. And then the last line, which is against my own procedure in a way, in some sense, you can't define 5D super Yang-Mills without also defining the 2,0 theory. Because this theory does not exist formally without specifying its UV completion. That's the mantra of field theory. So it's all sort of part and parcel of the same story. But what I was interested in myself was like, let me rephrase things slightly differently. What's the difference? I mean, normally when I UV complete a theory, I add in some degrees of freedom, right? That's what we were all taught way back when we were in grad school, like in the last century. And we were taught like, oh yeah, 5-4 theory is UV completed by electroweak theory, and you would add the W bosons in. But what does that mean in the strongly coupled? This doesn't make any sense to me. What it means in a superconformal field theory a non-Lagrangian field theory to UV complete it. You don't add new fields, do you? Something else must be going on. And what's the difference? What exists in 2,0 that does not exist in 5D super Yang-Mills? Okay, I should also mention various people's in the room's work, and I put it here because to me it's in a slightly different category than the others, because they require, well, perhaps Kim Young's work is very nice to be there. Most of these are 6D actions, and they suffer from the problems that were previously mentioned. It's too much to talk about them all in the 4 minutes that I've got left. So I apologize. Other things I would like to mention is how can we relate M2's to M5's? Then there's a few ways we might do it. One idea is T-duality. So in D-branes, if you wanted to get from a DP brane to a DP plus 1 brane, you just T-dualize. It's manifest, everything works, no problem. So why don't you do that for M2 branes? There is a sort of T-duality that takes an M5 wrapped on a 3 torus to an M2 brane transverse to it, and vice versa. It should more accurately be called a U-duality, but it's a T-duality. Let's call it T-duality. And you have a dual torus, whose volume gets inverted by this. And indeed, you should think that then M5's on T3 gives M2's orthogonal to it, and M2's orthogonal to a T3 gives M5's wrapped on the dual torus. The one important fact is that you have to do a decoupling limit. We're all talking about, U-duality is a duality of M theory, not of the brane actions. So you have to do decoupling, and what that means is you have to get rid of the Kluser-Klein tower of states, because they, of course, be Planck scale. All right, you do that by taking R to 0 and the dual torus to infinity. But that still gives you two relations, namely that the M5 brane on T3 of vanishing size should give you the M2. Okay, that actually, that's obvious, because taking the M5 on a T3, well, first you go down on S1, that gives you 5D super Young mills. You go down on 2 more circles, that gives you 3D super Young mills. You T-dualize, that sends the volume the other way, and actually it just tells you that the M2 brane is the strong coupling limit of 3D super Young mills. So you knew that. I'm still interested in the second way, which is you should be able to take M2 branes and take periodic arrays of them in the transverse space in a cubic array, and that should reconstruct M5 branes on the dual T-torus. So I wrote one paper on it with these authors a long time ago. It was an attempt, and the reason why it's difficult is because the stupid translational symmetry does not exist in ABJM. So you can't do the nice Oberfold that we do for D-branes. We did something different, and we got some modified version of 5D super Young mills out. This paper, I love it and I hate it. It doesn't quite work, but yet it has that grain of doing something for you. It all falls to pieces. It's a terrible calculation. And then at the end, the pieces all add up back together again. So like you take your jigsaw puzzle, you throw it up in the air, and then the pieces all land in place. It's like, okay, that's something, but whatever. You might consider doing a flux background. So you put on a background 3-form, and blow it up. And then these authors did the action from ABJM in this flux background, but they again found just 5D super Young mills. We wrote a nice paper showing that the monopole operator, which is the prescription from momentum in the M2 branes, maps to instanton type operators in this picture for the M5 branes. The last one I think it's the last one, is going back to BLG. Some people observed that if you took the Nambu bracket, this is an example of a 3 algebra, and you shoved it into the action, you would actually get an abelian M5 brane wrapped on some auxiliary 3 manifold. That's the 3 manifold that goes into the Nambu bracket. That's still, I think, not fully understood how this is working, what it means. Okay, so my challenge wish list, provide field theory definition construction of 2,0 without recourse to string theory or M theory. Right? That's the goal. In particular for this audience, you were looking at find the mathematical structures that best capture aspects of a 2,0. What are those? So you need to define apparently, non-abelian periods of 2 forms, and there's twistors and Lie2 groups, these sort of stories. So we want to obtain calculable formulations of 2,0. Well, with 6D diffeomorphisms of Lorentz, well, exclamation mark. As discussed, this is just, I don't believe it. It's not going to come. But okay, I'll put it here as a wish list. Construction action, again, what does that mean? But there could be families of actions. That's certainly, things that are valid in certain ways, or limits of them that are valid. Anything, something. partition functions, and I say functions because there's a certain point that there's not a unique partition function for this theory anyway. It's called partition vector. So, you know, I'll take anything here, but please give me the instructions that go along with it. Improve our understanding of quantum operators, you know, at a technical level as well as a conceptual level. So monopole operators and instanton operators. Well, this is a wish list. I mean, make S-duality manifest. That's sometimes always been the mantra behind the 2,0 theory. I think that's, personally, my prediction, that's pure fantasy. No. You can't always get what you want. You just learn to live with that. Make the n-cubed behavior more apparent. That would be kind of interesting. Okay, so I'm finished. I was going to give you the answer. There it is. And then if you had even more time, I was going to give you the action. But I'll be happy to talk to people afterwards. There's the action right there. And then you just, and there it is. But I've run out of time. So thank you very much.
Any questions?
And do you see how the cranial action with
That's right.
the 2,0 theory on the cranial pants action would come out of
The Trinion pants? What's the?
I think the 2,0, sorry, jet lag. Woke up at 4.
Yeah, me too. So.
Taking the 2,0 theory on this pants diagram that Toyota used to build.
Oh, sorry. That yes,
Because that's
yes.
not obviously something like it. There's no circle vibration there.
Yeah.
It's just there's some clever way to make it up.
I wish, but the obvious restriction of the 5D Super-Yang-Mills proposal is it only works on manifolds which have a S1. So let's even say you granted it to me, which is a big if, right? It only works if you have an S1 fibration. So you can do if it's just S1 times something, and it's 5D Super-Yang-Mills. If it's S1 sort of fibered over something, then there's these papers by Lindhanner and Olson and Cordova-Jeffries where you get Chern-Simons type term in the 5D action. And that's quite nice because there actually you can get chiral modes. And one of my slides I had to rush through is you get chiral modes, but they appear as solitons in the theory. But if it's completely like this trinion pair of pants, I don't know what you can do. I think there was some paper by Yagi, but I'm not sure.
So if the fiber is non-trivial, so you can take the two space to be like some kind of Riemann surface, like 2,0 Riemann surface. So if you reduce further, you get the 4D2D kind of duality. So the appearance of the Chern-Simons and all that, and then you have the boundary somewhere, and then you get the polarity. Can be done explicitly. So what happens when you have a fiber over instead of just a product space of a circle or a five manifold is that there's a walk metric that sort of represents this non-trivial vibration. And then you get in the 5D Yang-Mills, when you reduce on the circle, you get extra terms that account for this walk metric.
The derivative is not the trivial vibration?
Yeah, it is a non-trivial vibration. If it's a trivial one, then you get the regular 5D.
Yeah, what if it's not?
Not a vibration at all, it's just
Yeah.
a circle across normal.
No, just no. Like there's no circle inside.
Oh, no. Oh, then we don't have
Yeah. I would say, in some sense, I would say the 2,0 theory and Lagrangians, it's really a map. It's a map between manifold and Lagrangian, or field theory. Actually, let me not say Lagrangian. There's a theory, and you put it on a manifold, and it is described a quantum field theory on that manifold, and then you get different choices. And I don't think that there has to be the one for R6. That's true. I did. Thank you.